Okay, good afternoon everyone. Today I'm going to be talking about virtual network traffic shaping to ensure fairness in virtual WiMAX networks. This is a part of my master's thesis. The outline of the presentation that I'm going to give today goes like this. We begin with an introduction. And we give an overview. We begin with an introduction and we give an overview of the WiMAX base station and provide a few baseline performances. We then talk about virtualization, which proves as a motivation for the work that we do. The work is presented in the form of a virtual network traffic shaper. This is evaluated and then we present the future work. So the general overview of the project that is going on right now goes like this. The GENI project at WINLAB is aimed at deploying an open WiMAX base station. This should be available to GENI and Orbit outdoor users. Right now what we have is we have a base station, but we need to provide support for multiple users for this base station, and this can be done via virtualization. The scope and research objectives of the project go like this. We need to study and show the results of the baseline performance of the WiMAX base station. Set up an experimental, we set up the experiment setup for virtualization of the NEC WiMAX base station, and we perform a few experiments and show the evaluation. This evaluation leads to some problems in unfairness, which we try to solve via the VNTS method. So the WiMAX base station at WINLAB looks like this, where you have an antenna which is mounted on the roof, and we have the hardware present over here. A general block diagram can be presented this way. We have an ASN gateway, that is the access service network gateway that connects to the WiMAX base station, through which we have multiple clients that are connected to it. This is the current state of the WiMAX base station. One of the first tests that we wanted to do was to get a general feel of the coverage of the WiMAX base station. So we did a very simple test where we mounted a WiMAX mobile client into a car along with a GPS device and did a simple drive around WINLAB. So these are the RSSI values that are plotted. What we notice over here is that the RSSI values are really strong in and around WINLAB. And once we try to take the ramp over here, the RSSI drops and we lose connectivity. We eventually come back into connectivity and lose connectivity again. So we notice that there are some blind spots which are present. This can be explained primarily because the base station antenna that is present is mounted at a very low height. So it's mounted on the top of the WINLAB building, and the WINLAB building is not really high. So the coverage, I'm sure, would be much better if it was in a much higher building. The next experiment that we set up is we try to set up a profiling of the WiMAX base station. What we do over here is we take stationary measurements at 3 different locations. We choose locations that are at varying channel conditions and varying distances from the WiMAX base station. We choose location A, which is at around 43 feet from the WiMAX base station. We choose location B, which is around 291 feet. And we choose location C, which is around 680 feet. What we do over here is we perform stationary measurements. We keep the modulation and the coding scheme of the WiMAX base station to a particular fixed value, and we take measurements for different packets. Then the modulation and coding scheme is also varied, and the experiment is repeated for different packet sizes. What we try to observe over here is the downlink UDP throughput, and we vary the MCS and packet sizes like I mentioned. The result of these experiments go like this, where we notice that this is the average throughput and this is the location that we see, location A, B, and C. What we notice is that the modulation and coding schemes like half QPSK and 16 cam half, which are really robust, stay constant irrespective of the distance. Even when we move far away, we are able to see the rates that we see over here. The thing is, at 64 cam 5x6, which is the least robust but gives you the highest data rates, since this is the least robust, as we move away, we see the rates deteriorate gradually. And at location C, you see rates of which is in kbps. So that is not desirable over here. So having established a basic profile of the WiMAX base station, we then move on to virtualization. what is virtualization? Virtualization is a framework or a methodology of dividing the resources of a device into multiple execution environments. This is a prime requirement for us. We separate the environments for different users is not supported in the current infrastructure at this point of time, and this can be done by adding a layer of abstraction through virtualization. The technique that we use for virtualization is Kernel Virtual Machine, that is KVM. What KVM does is basically instead of using a different layer as a hypervisor, it uses the kernel itself as the hypervisor. And it introduces a guest mode through which multiple operating systems can be installed, and a completely isolated environment can be provided for different users. The main advantage of this is that it is supported by the kernel, and every time there is an update, we can take advantage of it. So to evaluate the KVM performance, one of the first things that we wanted to do was to evaluate the performance of KVM and see if this induces any unfairness in the performance. So what we do is, we noticed that this was there before. We added a machine on top with a KVM guest. We say 2 guests right now, and we do a one-to-one mapping to start off with. We have a KVM guest 1 that corresponds to the WiMAX client 1, and KVM guest 2 that corresponds to WiMAX client 2. What we do over here is send traffic, as a basic test, we send traffic from here to here and from here to here. The client 1 is sending increasing traffic from 3 to 15 Mbps. So it goes like this, and the first 10 seconds it sends traffic at 3 Mbps, then in the next 10 seconds it sends traffic at 6, and then 9, 12, and 15. While client 2 is always constant at around 10 Mbps. What we notice over here is that this is run at 64 CAM 5x6 and a packet size of 1024. If you notice from the previous slides, we notice that at 64 CAM 5x6, the aggregate throughput that we see is around 16 Mbps. And this is a point that we take away from that. And we notice that as long as the aggregate throughput of client 1 plus client 2 is below 16 or 15.5 Mbps, which is around the same time, both of them can get the desired performance. This stays when it is 3 and 10 and 6 and 10. But what happens over here is this guy tries to go to 9, and this guy is trying to run at 10 Mbps. So then the rates of the second client, which is running at 10 Mbps, drop in order to accommodate the other client, which is trying to get up to the rates. And then they settle at an even rate of around 7.8 Mbps, where they share the link evenly. So from what we can draw from this is that KVM itself doesn't induce any performance unfairness. This was done in a stationary environment. The next step was to see how the performance varies with varying channel conditions. Before that, we can look at 2 of the points that we know are desired for virtualized WiMAX networks. That is isolation. We need to ensure that the resource usage of one experiment has little impact on the other. And fairness. Fairness across slices needs to be maintained irrespective of the available channel conditions. What isolation basically means is that experimenter X and Y can both run their experiments independently without one's experiment affecting the other. And fairness ensures that the base station resources are allocated in a very fair way to both the clients. This can be based on an equal sharing or on a service level agreement that might have been decided before. So what we do over here is we try to create a scenario where we have varying channel conditions. For this, we choose a path that starts from the control room and passes all the way to the end of this corridor. We are in the large conference room right now, and we notice by walking around with a WiMAX client in WINLAB, we notice that this area has a varying channel conditions, as you can see over here. The RSSI value in the control room is around -50, but as we approach this area, the RSSI values drop. And this provides an ideal path for us to do the experiment. What we do over here is we keep client 1 stationary in the control room at -50 dBm, and we take client 2 along the path that is shown by the red dotted line. The results of this go like this. So this is the time plot over the time, the duration of the walk. The walk is this. It comprises of going from the control room to the end of this corridor and coming back to the control room. and the duration of the work is around 110 seconds. What we notice over here is that initially to start off, both the clients are around 7.5 Mbps. We are running this experiment at 64 CAM 5x6, which is the total aggregate throughput is around 15 Mbps, which is what we would expect when both of them are in good channel conditions. Then mobile client moves and he goes into unfavorable channel conditions and his rates drop, which is fine. And then he comes back into good rate and his rates go up. The intuitive thing over here, the interesting thing over here is that the rates of the stationary clients drop. This is not what we expect. We know for a fact that the stationary client is constantly sitting in the control room at a particular channel condition. And his channel conditions do not vary, but his rates drop. One of the explanations that can be given for this is that the base station resources, the first thing that I should actually be mentioning is that both of them are running at, they're trying to pump traffic at 10 Mbps each. Hence, they saturate the link. So there are all the downlink available resources at the base station have been used up, right over here. And then when the mobile client moves to a modulation scheme that requires more resources, it moves to a modulation scheme that requires more resources for the decoding. What we notice over here is that the downlink available resources are not there, and the scheduler of the WiMAX base station works in such a way that it takes away the resources from the stationary client and gives them to the mobile client. And hence we see a performance drop in the stationary client's rates. One very simple way to solve this would be through static shaping. We can say that we limit the offered load of the slice. We can ensure fairness in the performance of the stationary client by limiting the offered load for the slice. We calculate the throughputs based on the 50% channel time at the slowest MCS. What this means is, if both the clients are running at 64 CAM 5x6 and the maximum achievable rate for each one is around 7.5 Mbps, they end up saturating the link. When mobile client moves to a modulation and coding scheme which is at a lower value, if let's say half QPSK, based on our experiments that we did before, we know for a fact that at half QPSK the maximum achievable rate is around 3.2 to 3.3 Mbps. And over here, when client 2 is in half QPSK and it's trying to send data at 3.3 Mbps, it needs 100% of the channel. So this is something that we try to solve. What we do is we shape the client based on, we assume that the client is always in the worst channel condition. We assume that he's always in half QPSK. We know rates that correspond to half QPSK and we shape to 50% of that value. So what we do over here is we don't do anything to client 1 and we take client 2 and shape his rates to half of the half QPSK, which is around 1.6 Mbps. What we notice over here is this. We successfully managed to keep the rates performance of the stationary client constant, irrespective of the movement of client 2. And the mobile client, although it can achieve higher rates, we are shaping it, we are assuming the worst possible channel conditions, and we are shaping it to a rate of around 1.8 Mbps, and both of them stay constant. One of the conclusions out of these two experiments are this. So no shaping gives us better aggregate throughput. Aggregate throughput in the sense that when you notice the total available, the throughput that can be reached is around 15 Mbps. But when we do this, we get rates of totally around 10 Mbps, 10 or 9 Mbps. So we know that no shaping gives us a better aggregate throughput. Static shaping gives us a better fairness. This ensures that the WiMAX client, the mobile client is always using the resources that are given to it, and it does not eat up resources from the stationary client. So based on these, we can conclude a need for a scheme to adaptively control slice throughput. In the previous experiment in static shaping, what we had done is that we were assuming the worst case channel conditions. Assuming the worst case channel conditions for the mobile client limits the aggregate throughput that can be achieved by both the clients. This is not desirable. And for this, what we need to do is shape the traffic of the mobile client based on the channel conditions that he is operating in at that particular point of time.
So all this you will do in case you have two users where one user wants a mobile client and the other wants a static client?
No. So what we are trying to do is propose a general scheme. There will be mobile clients. WiMAX is the technology which we want to use for mobile experiments. And what we are trying to do is, irrespective of the number of users, we want to shape the shape based on the channel conditions that are present at the mobile client at that given point of time.
But if I am a user and I have an experiment which has both a mobile and a static client,
Right.
I would want to know how WiMAX would behave as it is expected to behave, rather than have some kind of a shaping, changing the way.
So the WiMAX scheduler as such does an unfair resources allocation.
So you're trying to fix the unfair.
Yeah, so we're trying to fix the unfairness that is done by the WiMAX scheduler.
We're basically trying to give 50% resource to each slice because of limited number of mobiles there, so only a few.
So as a solution to this, we propose VNTS, that's the virtual network traffic shaping. The basic goals of VNTS can be defined like this. We want to reduce the coupling between the clients by providing fairness in resources use. What this means is that when one of the clients is an unfavorable channel condition, we don't want to see any effect on the stationary client's performance. And at the same time, we want to maximize aggregate throughput while ensuring one. So we propose this architecture where we noticed that we had a machine over here where we had virtual machine running. This is a machine which has KVM running, and we have multiple virtual guests that are present. And what we have over here is the ASN gateway and the WiMAX base station. What we propose is a VNTS engine that runs in this machine and a VNTS controller that runs in the within the ASN gateway. What we do over here is that the WiMAX base station maintains a table or a database of sorts, an SNMP MIB, through which it can track the current channel conditions that any given client is in. So what we do over here is, using the VNTS controller, we send an SNMP query to the WiMAX base station. At a particular specified point of time, we do it at a regular interval, and we get an SNMP reply from the WiMAX base station that tells us the channel conditions of any client that might be associated with it. Based on this, we make certain calculations and send a command to the VNTS engine, which does the shaping. The VNTS engine basically is implemented with using the software Click, and what we have over here are queues that are coming in from the different users, from the different slices, and we shape them and send them out such that the link that is over here between the WiMAX base station and the client doesn't get saturated no matter what. So the architecture that we propose for the VNTS engine is implemented in Click. The primary functions that the VNTS engine is responsible for are separating the VM traffic. It needs to find out which traffic is associated with what mobile client to reduce the rate that it needs to shape at. It needs to provide all routing and shaping policies, and it needs to allow dynamic control of the virtual machine traffic. We need to be able to, we don't want to do static shaping that was established before. We need to be able to dynamically shape the traffic at any given point of time when we want to. So what we do over here is we get all the packets that are coming in from the host kernel, provide the necessary RPing, and send them to a classifier. The classifier separates the packets that are meant for each mobile client. Based on this separation, we shape the traffic and send them out through the Ethernet device to the WiMAX base station, which sends them out to the client. The VNTS controller, on the other hand, needs to achieve the following objectives. It needs to determine the channel conditions on the fly, which we do while using SNMP. It needs to detect saturation. The primary aim of this is that we want to avoid saturation of the channel. If the channel is not saturated, then both the mobile clients can exactly operate in the conditions that they want. If I want to increase my rate, then I have available resources if the channel is not saturated. So we want to avoid saturation in order to ensure fairness. So we limit the offered load per slice in order to avoid saturation, and we ensure that the resources used by the client is proportional to the weight assigned to that slice. So this, like I spoke before, the weight can be ensured that it is evenly shared. It can be a 50-50 proportion, or it can be a 20-80, or whatever one wants to keep it. So the VNTS controller algorithm goes like this, where we start off with checking if the available base station resources are less than the threshold. What the threshold basically means in this case is that we want to avoid saturation. So we can do a conservative shaping, conservative algorithm in the sense that if you assume that the downlink available resource blocks are 100, and what you want to do is when the available downlink resource blocks falls to 30, you want to stop and start shaping. This can be done by specifying this threshold value. Or you can keep it at 0 and it will just detect complete saturation, and it will do it only when the shaping can be done only when the saturation is reached. Then what we do is for each slice that we have, each VM that we have, we perform an SNMP get. What this SNMP get does is basically returns the channel conditions of the mobile client at that point of time. Based on these channel conditions, we multiply it by the weight that it is supposed to be assigned to. So if you want to give 0.2 to client 1, we get the channel conditions for that client, and we know the phi rate that it is achievable based on our previous experiments, and we shape it based on the weight that has to be given. And we send the set command to the VNTS engine, which implements this in Click, which we explained before. And this experiment is repeated at a particular interval of time.
I think you should explain what is AI.
Sure. So, okay. So what AI over here is basically we are getting SNMP get via AI. So what AI means over here is the phi rate that corresponds to the current modulation and coding scheme that is available for the client at that point of time. So if the client is operating in an unfavorable channel conditions, if he is in half QPSK, the maximum achievable rate, as we know from our experiments, is around 3.2 Mbps. And what we do is we get this rate and shape to the percentage that we want to give it. So that ensures that it gets, if you want to give it 20%, so we say shape to 20% of 3.2 Mbps. So this way we ensure that it gets only the channel that it is supposed to use, and not, it doesn't try to use the other person's channel. So the performance evaluation of the VNTS technique is done using, we define a few fairness indexes. We define a fairness index in the form of GENI fairness index. Through this we do basic calculations and try to find out the GENI fairness index. So what the GENI fairness index means is basically if you have 3 clients operating at a particular point of time, then the GENI fairness index, the minimum value for GENI fairness index can be 0.33. If it is like 2 WiMAX clients, then the minimum value is 0.5, and when the value is around 1, it shows that the channel is completely fair. So the first test that we wanted to do after having established a fairness index was to and set up the traffic, set up the system. We wanted to find out how the adaptive shaping works. So the adaptive shaping has these rates that you see over here are based on those outdoor experiments that we did at 3 locations. We find these rates out and we want to shape to these rates because we know these are the rates that are maximum achievable rates that are possible for each modulation and coding scheme. So we use these rates and we try to shape, run the experiment that we had run before and see what the performance looks like. What we see over here is that.
Get into the details. Did you already explain how you would determine these rates or percentages that are assigned to each slice?
Sure. So what we have for that is we try to maintain a small policy database over here at the VNTS controller, and you can assign weights to the clients as desired, and based on this, the shaping decisions are taken.
So the weights remain fixed at all times for all clients?
As of now, yes. But that is reconfigurable, and as in it is maintained in the form of a file that we can write.
It is fixed across the slice.
Right. Fixed across the slice.
But you should explain the philosophical interpretation. I'm giving you X% of the base station as a pseudo base station, which is cut 0.4 or 0.2, whatever. And so the rate you'll get whatever you get, like you put in a normal base station, but you'll only get pro rata to your
Why would you
so
change?
the X% of the aggregate base stations you do it at any given time?
not aggregate.
It's not aggregate.
X% of the time frequency blocks that we
X% of the time available.
The time frequency blocks that are available, the available resources at the base station.
should have had a slide explaining.
The aggregate throughput will be the time frequency blocks times the bit rate on each.
On each, yes. And that is for each mobile client.
Since the bit rate on each can vary, you don't want it
It's
to be
client
affected by
dependent, yes.
It depends on the channel conditions that they're operating at. So having implemented the system, we run the same test that we had run before, and we see the result that looks like this.
Sorry, one more question.
Sure.
In your algorithm now you have, can you go back to the algorithm?
Sure.
You have this AI times WI.
Right.
And the AI is the bit rate
That is
for
achievable.
one achievable to one client.
At that, yes, at that point of time.
So now you're calculating AI, so some percentage of the achievable bit rate to one client.
In the present channel conditions. That
And then you do set.
yeah, so we
set to.
set sends a command to the VNTS engine that implements this over here. So we send the command over here, the shaping decision, and it shapes the traffic based on that. So the traffic that the base station sees is only the traffic that is completely fair.
But how are you then assigning a particular time frequency block or a particular percentage of time frequency blocks?
We are trying to ensure the equal allocation of the time frequency block by shaping the downlink traffic proportionate to that.
Equal across clients?
That is reconfigurable. That is the WI that we spoke about. The weight. So that can be set to 0.5 if it's two clients.
So if I calculate bit rate times this weight,
Yes.
how is this related to this weighted splitting of
So-
the time frequency resources?
So what we notice over here is, let me just go back to. Okay, let me just explain it here itself. In fact, so what we notice over here is if the modulation and coding scheme is at 64 CAM 5x6, for example, the maximum achievable rate at that point of time is 16.1 Mbps based on our calculations, based on our experiments. So we know that if the aggregate throughput of all the clients combined is 16.1 Mbps, then the channel is completely
There
saturated.
will be a modulation per client, right?
Right. No, so irrespective of that, if we say, assuming that both the clients are in the same
All the
channel,
clients, yeah.
in the same channel, then we say that the aggregate throughput, if it reaches 16.1 Mbps, we have reached saturation. And the downlink available resources at the base station goes down to 0 at that point of time. Because if it had more downlink available resources, it would use that to generate more traffic. So we know that for a fact. And what we do over here is assume, we find out the modulation and coding scheme that the client is working on at that particular point of time, and shape based on the percentage of the bitrate achievable for that modulation and coding scheme. So if one of my clients is in 64 CAM 5x6 where the maximum achievable throughput is 16.1 Mbps, and the second client is in half QPSK where the maximum achievable throughput is 3.2 Mbps based on our experiments. To allocate the channel in a fair way, we would shape this guy to half of 16.1 Mbps, which would be around 8 Mbps, and we would shape this guy, the other guy who's mobile and is in half QPSK, to 50% of the achievable rate at half QPSK, which would be around 1.6 Mbps.
An approximation that is partly because it's the black box. If you had control over the time frequency block, you can directly assign from a slice to the time frequency. Here, the base station is a black box which has its own achievements. It's trying to do virtual thing on top.
Are you assuming that all these packets are the same size or are they different size?
No, they can be of any size.
So how do you do mapping from packet size to this modulation encoding?
So we irrespective of the packet size, we shape the available traffic that we see at that for that second.
Yeah, but is that going to be really fair because.
So we explore
they are
that
different
through
sizes.
further tests. We do some experiments and try to see the impact of packet size, if it has any, on the scheduler. The results are presented in the following few slides.
Okay, why don't you go ahead? Sure.
So what we see over here is this. We notice that the mobile client, as before, goes into an unfavorable channel condition and his throughputs drop. But the stationary client is now able to stay in and around 6.8 Mbps to around 7.5 Mbps, which is the rate that we would expect to see. So what we achieve over here, basically through by implementing the VNTS traffic shaper, is that we manage to allocate the resources in such a way that the stationary client's performance is not affected by the channel conditions of the mobile client.
They are now using the same encoding scheme or different?
The same, no, so over here, that depends on the channel condition. The path of the walk is this. So what we see over here is that we're taking a walk from the control room all the way to the end of this corridor and back. What we noticed in this corridor basically is that in this region, the region which is shown by green, there is a variation in RSSI. As there is a variation in RSSI, the modulation and coding scheme shifts accordingly because we have adaptive link adaptation enabled. So based on that, what it does is it shifts to the modulation and coding scheme that is best for that particular channel condition.
So client 2 will change.
Client 2 will change. So we observe that even as the channel for the mobile client deteriorates, the base station utilization is appropriately limited via shaping, thereby preventing any performance in coupling with the static node slides. The next thing that we wanted to check was if the rates that we are using and the rates that we have achieved, these rates that we have achieved through the experiment are conservative or way too unconservative. What we wanted to find out is by varying these rates, can we get better fairness? Can we get greater channel utilization? The two of the parameters that we are concerned about at this point of time. So the next experiment that we wanted to do was vary the policy. The policy goes, if we have 100% of the channel condition, 100% are the rates that correspond to this, then we try to shape at rates which correspond to 80 and 90% of the experimental values. And we try to see the performance, we measure the GENI index and the aggregate throughput and try to see if making the rates more conservative has any impact on the performance. So what we notice is this. We see that in a no shaping policy, the fairness index is around 0.67, and by implementing our shaping policy, we are able to bring it up in the bracket between 0.8 and 0.85. We use different shaping policies. We shape at experimental values, then we shape at 90% of the experimental values that we have, then we shape at 80% of the experimental values that we have. We notice that there is not much difference and we are successfully able to maintain it regardless. And we also notice that the rates that were set by the experimental values give us the best performance. Then we look at the aggregate throughput. The aggregate throughput is an important factor too, and we check over here that the aggregate throughput stays around the same. It's just a little higher for no shaping, which was expected. But using the shaping at the experimental values that we have reduced, we are able to keep the channel utilization in and around the same area as that of no shaping. The next experiment that we wanted to do with this was with regards to packet sizes, like we spoke. And we wanted to vary the frame sizes, and we vary the frame sizes at 128, 256, 5112, and 1024 to see if this has any impact on the algorithm that we propose. So initially we said...
Sorry, but when you say that you vary sizes, they are varied across the different clients, but not within the client stream. So
that was the first experiment that we did, and the second experiment that I speak after this keeps one client at 128 and varies the other client to see if the change in...
Okay, but can one client send for a while at one size, packets frame size, and then after a while it switches to another?
Definitely. That it should be respected. So the results that we see based on this should explain to us that varying the packet sizes does not have too much of an impact. What we see over here is this. At packet size of 128, 256, 512 or 1024, we are still able to maintain the fairness between 0.8 and 0.85. And the aggregate throughput, as you would expect for 128 byte packets, would be much lesser than the others. But this is still acceptable because we can maintain the GENI fairness index regardless of the packet size. This is when both the packets, when client 1 and client 2 are simultaneously transmitting at 128 byte packets and then 256 and then 512 and then 1024. The next experiment that we wanted to do is we wanted to check if the variation of one client's packet sizes affect the other. And this was done with this. So what we do over here is we keep one of the client's packet sizes constant at 128 bytes at all points of time. And if we vary the other client's packet size from 128 all the way to 1024. And what we see is a very similar performance to the previous graph. This and this. So what we see over here is, even over here, we are able to maintain it in the bracket that we have defined as fair. And the channel condition performance also is very similar to what we see in the previous graph.
It's kind of strange because, I mean, when you change the packet sizes, it's, I'm not sure that you can, because your algorithm looks very simple to map from, I mean, to allocate the resource. So you just do this multiplication, AI times WI.
After getting the channel conditions, yes. As of now, we've kept it to that. We're trying to do more experiments.
I would assume you would need to use some kind of fair queuing or something, no? You don't need to.
What we've noticed is by doing the simple thing and measuring the channel conditions at the packet size, we can successfully allocate the resources in such a way that the performance of one client doesn't affect the other.
What is the frequency of link adaptation?
Sorry?
What is the frequency of?
The frequency of link adaptation is around 200 frames, once every 200 frames.
If you change the packet size,
Right.
and if you do it every 200 frames,
Right.
then you are actually here affecting the link adaptation, and therefore you might see such throughput.
Right. Yeah. So that is what we're trying to say over here. One of the having established this, we can say that the VNTS mechanism works irrespective of the frame size that is used across the flows. And the next experiment that we did was to assign weights to different clients. So we have two clients in operation at this point of time. What we do is we assign a 1:1 fairness ratio in the beginning, then we move to 2:1, and then move to 5:1 and 10:1. So what this basically means is from the available link resources that are present, we assign 1:1 in the beginning and then try and increase this and see if this has an effect on the performance. So what we see over here is that this is the GENI index, and the GENI index is pretty much constant around the area that we defined. The aggregate throughput definitely increases because we are trying to shape the mobile client to values which are much lower. And as we increase the shaping ratio, as we make the shaping ratio a little more fair, the throughput rates are higher. So the conclusion of this talk basically was that the proposed technique, based on our experiments, we can say that the proposed technique works well with the usage scenarios that are considered: varying loads, varying packet sizes, varying channel condition, and varying flow weights. There was an unfairness observed in the amount of resources that were allocated to each slice, and this system helps correct that while ensuring a reasonable channel utilization. For future work, we know that we have to implement intra-slice fairness and scheduling. What this basically means is we want to be able to have one slice that can associate to multiple clients, and we want to be able to maintain fairness even in this scenario. And we need to try and understand how the base station scheduler affects the performance of our shaper and make some decisions based on that. Further evaluation of the VNTS needs to be done with other traffic types that are mentioned, and we need to optimize the traffic shaping parameters based on these experiments and deployment that we propose to do.
I'm not sure.
Thank you.